Werneck. I'm a postdoc at the University of Idaho. I work with Zach Etienne on NERP stuff and more recently on Grail, which is a Germ HD library that is going to be, it's a refactored and a reworked version of Illinois Germ HD that we ported out of the toolkit and now we're porting back in, and it's also going to be infrastructure agnostic. And I'm going to talk to you today about simulation analysis. So it's going to be more of a talk than an interactive tutorial. There's still a lot of instructions for you to follow later, but it's mostly reading and taking a look at a few things. So I feel like, especially for the new students, whenever you join a group and they share with you a parameter file that works for the Einstein toolkit, even if you know nothing about it and all they ask you to do is go and run a simulation. Yes.
Do you want to be sharing that screen?
Am I not? Oh, I'm not. I'm sorry. I saw that it was there and I just didn't. Yeah. Okay. So I feel like if you're a new student and you join a group and they share with you this parameter file and they say, go do some simulation, then you might be able to compile the toolkit and run it. But then as soon as someone asks you to change something in the parameter file or do a different simulation that does something slightly different, it's often very difficult to configure the toolkit again. And I feel like these parameter files organically evolve into something that, every time someone touches it, they add something to it or they modify something. And in the end, nobody really knows what's happening. So I'm pretty confident in saying that if I had to write a thorn from absolute scratch, starting from an empty file, I could probably find a way around it. But if I had to write a parameter file to run a binary neutron star simulation, I cannot without copying it from somewhere else first. And so I figured that I'm going to take a few minutes to discuss a couple of parameter files with you guys that I simplified significantly from what they usually are whenever you receive a parameter file to do a binary black hole simulation, for example. And so I figured that it might be useful to talk about how do we set up and what does it mean when we need, what do we really need to set up something like AH Finder Direct to find black hole horizons, and something like quasi-local measure to compute things at the horizon, like spin and mass. So I hope my font is not too small, but I'll try to keep it a little bit bigger as needed. This one I know is tiny, so I will increase this one too.
I don't think
You're not sharing that screen.
Am I not?
no.
No, this
You
is
shared the application.
Of course I did. I shared just I didn't share the entire screen. Okay. All right. Hopefully now, can you see this now? All right. Okay. So so I created a repo for this for this tutorial. And it's in my personal repo, so it's GitHub Leo Werneck, and it's going to be RIT School, or you can go to tinyurl analysis ET 2023, which will take you to this repo. And in the repo, there is a wiki, and the wiki starts off. Let me move this around a little bit. It starts off very modest, but then as you click here on diagnostic thorns, there's some documentation on how to set up a couple of thorns for these things. And then the second part of the tutorial will be mostly I guess a Qubit advertisement from a poor man's perspective, because I don't know a lot of the things in Qubit. And so, for example, I'm going to use Qubit to compute things that are not generally available in the grid functions from Illinois Germ HD. But then in the end, I'm not going to use Qubit to generate the plots because I don't know how to do it. So I'm just going to do matplotlib. And then because most of the clusters I work with do not have ffmpeg, that's not built in the script either. It's a separate command. So it's going to be kind of a mess. But that's what I normally work with every day. So I feel like it might be useful for people to actually learn these things instead of the neat things that work all the time, but then never work in practice. So, so I'm going to start with these parameter files. And these are already, sorry, that's not it. These are already in the repository. So later, if you want to, read them and run them, you're free to do it. So this first one is just a parameter file for a single puncture black hole. So it might be surprising for those who have ever done a simulation with the toolkit that I could enable only 19 thorns to just do something that sets up initial data and dies, but it's still, that's what you need, right? And the worst part is that, I've written a little bit of something that usually reads in these things and organize them and sort things around. And so at the bottom, it tells you how many thorns you have to activate, but don't have to set up. So there are no parameters for these thorns anywhere in the parameter file, but if you remove any of them, the code won't run. So you just have to have them along and you have to guess that they need to be there, right? But that's just how it works. So I'm going to try to describe what each of these thorns do. And I know that for some of them, I don't really know, but we have people here that might be able to help. And so, so it will be useful. I'm going to try to go sort of, at least in a few places in the profile, I'm going to go sort of line by line just to explain a little bit about what these things do. But then in other parts, I'm just going to go a little bit quicker because it doesn't matter. But if you're brand new to the toolkit, these is all alien probably to you. So I'm just going to go a little bit over. So ADM base is the thorn that sets up. So this is a single black hole parameter file. So it's going to set up a metric. And ADM base is the thorn that provides metric grid functions for us. So this contains, for example, the lapse, the shift. So that's also something I need to say. So my keyboard is falling apart. And so when I press most keys, it types in 2 or 3 times that key. And then the shift doesn't work sometimes. And so sometimes I meant to close a parenthesis and I type a 0 or something. So bear with me. The shift vector and the spatial metric and extrinsic curvature. AI local interp is an interpolation thorn. I actually use it manually in some thorns that I've worked before. It's used to, for example, if you want to interpolate an actual grid function with all the AMR that's going on, you need an interpolator that knows how to do that. And this is something that comes with Cactus as far as I know. But the problem is that you see down here that you also need the carpet interpolator. And if you try to remove one or the other, it won't work because apparently some thorns need one and some thorns need the other. I don't know which one needs which. And so I need to activate both. I think that carpet interp is only necessary for quasi-local measures because that's where I get the error. But it still needs it. So I needed to activate it. So this provides interpolation for AMR grid functions. I'm going to try to keep it somewhat short. And then this one is basically the same. I don't really know how to distinguish them. People can let me know if so this is so then we have AH Finder Direct. So this is so it's a thorn to find apparent horizons on the grid. So if you as we'll see later down in this parameter file, you provide a guess of where you think your black hole is or where it will be. For example, if you have a binary neutron star simulation and you expect a black hole to form near the origin, you tell it where you expect the black hole to be, provide a guess for the shape of the black hole, and it will try to find it for you. And if it does, great. And if it doesn't, you waste a couple hours trying to figure out why it's not working. So this boundary thorn is the one responsible for letting carpet know about the boundary conditions of grid functions. That's what and I don't think it's responsible for symmetries, but for the sake of this parameter file, it's just enabled, but it's not configured. So this, I might be wrong, but that's what I think it is. Carpet about boundary conditions. Might also tell something about symmetries. So this is the main driver. It's carpet. It's the one that provides AMR and all the communication between the grids as far as I know. So it's the one that will do the most. Then this is one of the output thorns. So unfortunately, I ordered all the thorns alphabetically. They're not particularly grouped together in a neat way. But IOASCII is the thorn used for input, output of ASCII files. So for those who are brand new to the toolkit, if you want to output 1D data. So if you want to see what the labs looks like after it was set up, that's the thorn that's going to write it to disk so that you can see. There's a sister thorn of this, which is called Carpet.io HDF5, which produced the same type of output but in HDF5 format. Yeah. So this one, Carpet Reduce, is used to perform reductions on the grid. So if you're doing AMR and you have these multiple levels, and you want to compute, for example, okay, what is the sum of all the points of a certain grid functions on the grid? You typically don't want to double count in regions where the grids overlap, and then this thorn will take care of that for you. You perform these reductions, the sums, or find the maximum or find the minimum of grid functions, even across multiple MPI processes. So this one performs reductions, min, max, average, sum, etc. on the grids. Then Carpet Regrid 2, and I'm guessing the 2 is version 2 and historically just stuck, is the thorn that actually enables us to specify what is the AMR structure that we want. So this thorn is the one that we're going to use to say, I want a center at position XYZ. I want this many refinement levels on that center, and I want the radius of the radii of those refinement levels to be 1, 2, 3, 4, something like that, right? So this is the thorn used to set up the initial AMR grid. Now these 2 thorns, I don't know why we need 2 of them. I can kind of understand that one just provides the coordinates and then the other one just sets Cartesians, but I think one of them doesn't require any configuration and the other one, but I feel like they're both kind of doing the same thing. They're just saying set up a grid or something that has, you know, this range. Maybe people can correct me if I'm wrong, but basically this thorn chord base is the one where we say, so we set the grid extent and step sizes. And this one, I guess, enable Cartesian. I don't know what this one does. Maybe Roland can help me with that. I don't know what it does. Yeah.
Okay, so the thorn predates me. It's Cartgrid 3. And then go off from the main grid. Whatever. So Cartgrid 3D actually provides you with coordinates for each of the grid points. So there's these X, Y, and Z coordinates that are coming from that.
Fair. But they're all specified in the other thorn.
No. The other one describes to you your grid extents. Says it goes from A to B, but it doesn't actually give you the coordinates.
Oh, okay.
So that's the difference. Okay. One describes the grid as a whole. The other one really just nowadays just provides you with the X, Y, and Z coordinates.
Okay.
Historically, it also had the ability to have a certain sort of symmetries. You could apply reflection symmetry. But these are deprecated by now in favor of the reflection symmetry thorn.
Okay.
If I'm right, the Cartgrid 3D is the one that's called grid when you inherit, right? Or yeah, so Cartgrid 3D is the grid.
That's nice.
One. So whenever you say inherits grid or something, it's that one. What?
Okay.
Yeah.
Because you're going to see that a lot when you try to develop thorns, and whenever you open something, there's always an inherit grid, and that's probably what gives you access to XYZ, and so that's the one, right? So this is the okay, and this is the one that kind of annoys me, right? We need to enable the method of lines, even though I'm not doing any evolution, and there's no evolution thorn active, but I still have to do that because I guess this is what sets time or DT or something. I don't know why I need this, but
probably need more post-step groups or something like that.
okay. Not used, but still need to be active in this part file. Normally we do use it, but in this part file it's not used. So, and then because, you know, I was the one that wrote the ET version of NeurP elliptic, of course I'm using that instead of 2 punctures just because, you know, why not? So this will provide the puncture initial data. And then it messed up the spaces, so I'm gonna fix this just a little bit. Okay. All right, then quasi-local measures will allow us to compute. So it's another diagnostic thorn. Computes integrals on surfaces. Then I don't know. Okay, I'm gonna maybe put like this. Yeah, this is kind of a diagnostic. So this one sets up spherical surfaces. So this thorn sets up spherical surfaces that are not where the evolution happened, right? So if you want, for example, to extract gravitational waves, or you want to compute the ADM mass or the ADM momentum on the grid, usually what you want to do is you want to compute a surface integral at infinity. Of course, our grids don't go to infinity, but you can place a spherical surface with a radius that is basically the size of your biggest grid, and then you can ask quasi-local measures to perform an integral in that spherical grid. And so they go hand in hand. Spherical surface is something that both quasi-local measures and AH finder direct depend on, and also other thorns like multipole and Weil scale 4 for computing gravitational wave and extracting gravitational waves. So static conformal, I thought we got rid of this in the previous release, but apparently we didn't. So this is here for historic reasons, apparently, and nobody uses this, but if you don't activate it, it dies. So it's there. So this shouldn't be here, but it has to be. Because there are three things that depend on this. It's AH finder direct, quasi-local measures, and TMU base. And these three things die. When I remove it, the error message says that these three things needed. So we're gonna get rid of it, but for now, it has to stay there. Then symbase is the base thorn that tells what the symmetries for the grid functions are. So if you want, we're not doing this here, at least unless the defaults tell it to do. I don't think they do. But we're not imposing any symmetries in the system unless they're done by default, but I don't think they are. So this is like reflection symmetry or like rotational symmetry, etc. And then TMU base is the one that provides us energy, momentum tensor grid functions, which for this case, it only needs to be active, like we're doing black holes, and so this is vacuum space-time. But we need TMU base because quasi-local measures requires it, even though it's not going to be doing anything, unless there's a parameter that I could have set that doesn't error out, but otherwise it's a requirement. Even though I'm not going to declare any storage for TMU or anything, it still needs to be active, otherwise it won't work. Okay, so there is one thing that I usually find a little bit annoying, but I guess it's just the way it is, right? You can see that when I activate all of this, there is no cactus or flesh thorn in here, but still we do have access to that. And that's how we say, what's the final time or what's the final iteration from our simulation. So again, that's something that eventually you pick up on, but it's not obvious at first. So the only set that I really stripped down this to the most bare bones that I could. So this will not be useful for any production level quality work, but it hopefully will give you an insight of how to set up a few things as easily as possible. So the only core parameter that I'm setting is I want it to die at iteration 0. So it's going to set up the initial data and stop. It's not going to try to do anything else. So for ADM base, the only configuration that I'm going to say is I want the initial data thorn to be, so if this, okay, I'm going to put here the comment as well. Stop after iteration 0. So this just means that NERP, so NERP elliptic T will set, even though it's maybe not obvious, but it will set the metric, lapse, and shift. And it might not, I don't know what the lapse will do actually, but I think it will set the shift will be 0, so I don't really mind. But yeah, it will, I would put it at least these two. At least these two I think is true. And then this, oh yeah, of course. It will set the metric, and then NERP elliptic T will set the lapse. So that's all that it means. Everything else is not shown here, so it's not obvious what it's doing, but everything else basically defaults to 0. So the shift is going to be 0, the time derivative of the lapse is going to be 0, the time derivative of the shift is going to be 0. But again, I'm not going to bother with that because I'm not trying to evolve anything. I'm just showing as little as I can to get to the actual diagnostics part. And then this is the NERP elliptic configuration. So this is where I say, okay, I want you to set up a binary black hole for me. But because I'm only interested in having one black hole, I'm setting the mass of one of the punctures to 0, which we can do, even though it's a little bit of cheating. And then I'm reducing the number of points that are used in the radial and angular directions in the thorn so that it runs faster. I only wrote this here because it's worth explaining. Otherwise, I'm going to use the parameter like I'm using down here, and it's not going to make any sense. But this, so NERP elliptic doesn't solve, it again uses separate grid to solve the initial data, just like two punctures or food or everything else. And the grid that it uses is like a bisphere. So you have two foci where there's a lot of resolution around it, and then it just spreads out and you lose resolution as you increase the radius. And so this just tells us where to put those foci. It can be anywhere on the grid. So usually what you want to do is you want the punctures to be at the foci, at least while you're solving it. And then later on you can shift them. So you can always find a way to make it symmetric about the origin, even if they have different masses, and then later on you just shift it to the center of mass if you want. But in this case, so this is yeah, I'm not doing that here. I'm actually leaving it at that position. So this is the default parameter. It's usually set to 5. I'm just setting it there, like I said, just so that it doesn't appear out of nowhere. Setting the bare mass of one of the punctures to 1/2, the other one to 0, and then I can set the position of the puncture to wherever I want. In this case, I'm just setting it to the x position, which is the y, the 0 component of this position vector, to be at the foci exactly. And I'm only setting the spin of the puncture in the z direction to be 0.2. Everything else defaults to 0. So it's going to have no linear momentum, and the spin in the other direction is going to be 0. So that's that. So this basically just sets up initial data. So it's going to be single puncture initial data located at x, y, z equals 5, 0, 0 with mass 0.5, bare mass. Okay, that's saying a lot. Oh, and spin 0.2 of the z direction. So there you go. So this is a lot of words to just say this. This is all that this is doing. Okay, so now it's where we set up the grid. I feel like a lot of people are interested in setting up the grids initially, and they have no idea how to do it. This is one way of doing it. So just forget about these three. I don't know what these three do exactly, but if you don't set them, just focus on the AMR for now, okay? So on the AMR, which is it's what everyone wants to see,
Well,
right?
I mean, the initial time levels, you may want to.
Yeah, okay. So the initial time levels just tells you to fill all the other time levels with the same data as the.
Right, which
Right.
is potentially a source of error, so.
If you don't
you're-
set it, it will error out. So.
No, but initial time levels does an order, order delta, makes an order delta error in the prolongation region, so.
Right.
Am I correct? Initial time levels just copies the data to the past time level, right?
Yeah, that's just the initial data time. But
Yeah.
propagation order time 0 is yeah.
Yeah.
But no, but so I'm just saying that if you're trying to do a very accurate simulation, you might not want to.
No, you don't want any of this for sure.
Yeah, so time level. Yeah.
It's not production at all, right?
I'm just saying, like, as that parameter.
Yeah, no. Yeah, I mean, the usual carpet configuration has like multiple times these number of lines, right? But this is just the bare minimum that I could set up. So I'm setting prolongation order in time to 0 because implicitly the number of time levels for the metric is 1. And if you have anything greater than 0, it will need more to do the interpolation, and so you can't, right? So I'm kind of cheating a little bit here, but so I assume that when you set it to 0, that just means that it copies everything when prolongating. It's like a restrict, but yeah, anyway. That's why I said ignore all this, doesn't matter, right? What you want to know is how many refinement levels can I stick in there, right? So this is the parameter that sets it up. So you say 11. Are you forced to set? So does this mean that you spanned 11? No. It just means that the maximum you're allowed to do is 11. But carpet does not create the grids. What creates the grids is chord base, as we'll see later on. So this always has to be like this as well. Isn't that true?
This one, yeah, well.
I mean, this doesn't mean anything. Like you still can have fewer refinement levels than what you said here.
Yes, and everything that we said was correct, except chord base does not fit the goods. Carpet record 2 does.
That's fair. I said the wrong thing. Yes, yeah, that's fair. Yeah. Okay, and then this one, just have to set it to chord base. That's not the default value, so it needs this configuration. I don't remember. I think the default is box, which I never used. Yeah, I don't know how to, yeah, anyway. So, okay, so this is the part that might be a little bit unintuitive. So chord base provides all the specification for the grid at the courses level, right? So you have to do the math a priori to figure out, okay, if I have 11 refinement levels and I want this resolution at the finest one, you need to propagate that back and set it up so that this value here that you use is the value at the courses level. And then when you divide it by 11 times, you get the desired resolution at refinement level 11. Okay. So in this particular case, I'm setting up a grid that spans from negative 1024 to 1024 in all directions. But that means that if I do it that way, I'm going to have 0 on my grid. I don't want that. And so I just shift the grid a little bit by I know that probably most people don't do that. There's an avoid origin parameter somewhere, but we usually do it explicitly. So I just did the same here. So by just shifting the grids a little bit in one direction, I can ensure that it doesn't cross the origin. And I do it by shifting it by half of the x in the finest level, just because that way none of the grids hit it. But anyway, so this just you could imagine that it was just like this for the sake of clarity. That's I don't even know if I need this because I think NeRP elliptic is robust against this, but there are some initial data torrents are not.
I think it works better if you call it inside a half integer Bessel function.
There you go. Yeah, if I do it like that, it might be easier to understand. I don't think this is a problem with NeRP elliptic, but all of our TOV solvers don't support this, because we usually don't have data that go below like a certain radius. Not all TOV solvers in the toolkit, but the TOV solvers that I'm used to working with. And so if you put a grid that actually has a point on 0, you can have problems with the initial data. So I typically should tend to avoid that, even though none of the evolution don't really care about it as far as I know. Okay, anyway, so I would try to leave it like this, and if it errors out, I'll fix it again later. So now you told the toolkit, okay, I want this many, so how many grid points are that, right? And this is something we can do. So it's 1024 times 2 divided by 51.2. So that's 40 points on the courses level, right, that you're going to have. So this is a 40 cubed grid. And then as you keep going on and as you keep going down, I am having the extent of the grid. And as we go down, we are also having the step size. And so you're going to have a bunch of 40 cube grids all the way down to this little grid of radius 1. And the resolution at the I actually don't want to do that. Let me see if I can do that. Nope, that's not it. That's not gonna work. Anyway, I can, let's see. So if it's 51.2 divided by 2 to the 11, it's going to be, oops. So that's the resolution that's going to be in the finest grid, right? Yeah. So just in case people want and then, but anyway. Is that not right?
Yeah, I was
It's
gonna
not
ask,
right.
it's
No,
always
no,
the
no.
counting gets a little,
Yeah.
yeah.
You might not
Grid
be
number
right.
11 is number 10.
You might be 10. Yeah. Okay. There you go. Yeah, and that probably makes sense because if I divide 2 by that, it should be 40. There you go. So the resolution is actually that way. Okay. So that's, I mean, I usually have a little spreadsheet that just computes these things for me because then, right. And then, so there are multiple ways of setting this. I didn't know this a while back, but one very common syntax that I always see is instead you do like this, right? You say, oh, the radius of refinement level 1 is 12, and then you just copy a bunch of these and you go, the radius 2, 3, 4, and that might be easier for some people. If you prefer to do it this way, it works just the same. The syntaxes are equivalent, but I prefer the one where it's in a one-liner. It might not be as obvious. And of course, I don't know, does this support if I set this to the same extent, or it doesn't work, right? Oh, it's ignored. Okay. Yeah, I didn't know it because this, yeah, the only annoying thing about writing it in this form is that you have to put something here, I figure. Or can you do this?
I don't think that will work.
Yeah, exactly. Like that's the only annoying thing, right? Is you have to put something here, but even though this is not doing anything because this value is actually read from here. So even if you put something like 0, it doesn't change the fact that the outermost grid will have an extent of 1024. But anyway. So, but this is where you basically set up everything, right? You say, I want one refinement center. That means that there's going to be just one center with a bunch of levels in it. I want it to have the same number of refinement levels as the maximum allowed by carpet. So that's why I set it like this. This is something that maybe some people don't know that can be done as well. You can use parameters that already appeared in a parameter file. Or at least the ones that are not going to be set later on. So long as you don't write to this parameter anymore, you can always use it. And so that way you can change things in one place and the whole parameter file is updated, and that usually saves you a lot of trouble. So in the same situation, I'm just setting it here to the same place where the foci of my coordinate system is. So it will be located in this case at x equals 5. And I didn't have to set these two, but I just figured that it would be worth saying. So this creates a single grid. Oh, I don't know if I could write it. Is that correct? It probably isn't. Hierarchy. Yeah, go write hierarchy. How do I write hierarchy? Hierarchy. There you go. Yeah, there you go. I still don't know what's wrong with what I wrote. There you go. Okay, centered at foci with refinement levels in radio specified by this variable here. Then in the next example where we're going to do a binary black hole, you see that creating the next grid is just as easy, right? You just copy this, put it whatever you want in the grid, and then you just change the number of centers to 2. And that will create 2 refinement levels. 2 centers then, and we can visualize this later. So this is all you need as far as a grid is concerned. And then we have the diagnostic parameters. So for diagnostics, in this case, I'm only setting 3 thorns, I think. Yes. So I'm only setting spherical surfaces, AH finder direct, and quasi-local measures, only 3. So spherical surfaces is the one that the other 2 will rely on. So like I said, it will create the spherical surfaces for you at a given radius if you want, or it will just allocate memory for a spherical surface and then let another thorn finish the setup for you, which is, so I decided to do both just to show an example. So I'm setting up spherical surfaces here with 2 surfaces. And for both of these surfaces, I'm going to set the number of theta points to 81 and the number of phi points to 120. Note that the actual values of n theta and n phi that you use here don't need to match the maximum, but this way I just need to edit one place and it will change everything. So I decided to do it this way. Then you can set up the radius of the 2 grids. And the first one I set to 0 because I have no interest in setting that. I just want 2 punctures to have a grid to be able to, sorry, not 2 punctures, AH finder direct to have a grid to be able to put the horizon data in. But the other one I actually will set. And I set it kind of weirdly here by saying it's the negative value of x min. And the reason why I do that is because originally I had shifted things a little bit. So if I use x max instead, the radius will go out of bounds and I won't have data in there. So I use this because x min is shifted inner a little bit. So anyway, it's just a quirky little thing, but you can set this to whatever value. Like if you want to set this to 512, it will still work. And then this is what tells really the thorn to either set up a grid, a sphere, or just allocate memory so that another thorn can do it. So the first one, I'm not asking the thorn to do anything to it, and the second one I'm saying, please do. Right? So this. It sets up 2 allocate spherical surface grids with 81 by 120 points. One grid first is left for page finder direct to set up, while the second one is set up by this one.
And why can't they use the same grid?
So Age Finder Direct is going to try to find a trap surface, a closed surface, and it's going to find an apparent horizon. Let's say you found an apparent horizon. It needs to store the shape of that in some sort of surface. So it will do that on the first surface, let's say. Now, the second surface, I put it at the outer boundary because I want to be able to compute, for example, the ADM mass that is on my grid. So if they use the same surface, they have to have the same shape as the horizon. Otherwise, you're not going to be able to. So if you're interested in just doing things at the horizon, you don't even need the second one, right? But by doing it this way, you can set one that, it has a free radius because the Age Finder Direct was set that to wherever radius it finds the horizon to be. And the second one is I manually fix at a radius of 1024, and I say perform the intervals there so that I know what things are. So yeah, and then we go down to Age Finder Direct. So much like spherical surfaces, it can find multiple horizons. It's not limited to one. In fact, I think the limit is very high. It's like 100 horizons, if I'm not mistaken. But you have to say how many horizons you expect to find. So in this case, it's a 1. And then I don't know what move origins is. I was playing around with this a lot, and without setting that up, it doesn't work sometimes. So it defaults to no.
So move origins is critical if you have black holes which are moving.
Okay.
Otherwise, it's only going to look for horizons at
Fixed location or something.
500 for all time,
Oh, okay.
and that is such that might not be a possible solution. For example, the horizon's over here. Am I correct in this?
Yes.
Yeah.
500 you're taking because that's the Toolkit position?
Yes.
Yeah.
Okay, yeah.
Yeah. So like if you have it here and you have a horizon there, the algorithm itself cannot find that horizon because the rays that pass one angle ray will actually pass through 2 parts of the horizon. That's not allowed for a point to direct. Okay, so
yeah, so without doing this, I could not set it up, but yeah, so that explains it. And then here I tell Age Finder Direct where I want, which spherical surface I wanted to store the horizon data. And so I wanted to store the horizon data on the spherical surface indexed by 0, which is the first one. However, for some reason, the first horizon is not the 0th horizon, it's 1. And I don't know why, but I mean, it has the 0 in there, but apparently it's not used, right? It's the only thorn that I know that does that too. but yeah, it does that. So you need to know this. So
it's called the first horizon.
Right, but the other one's called the first surface too. But anyway.
Yes, but why would you call the first surface? Why would you label the first surface with a 0?
I suspect this is a Fortran torn, and that's why one is
no,
used.
No. This is just a convention.
So yeah, so this sets up the Age Finder Direct to search for a single horizon initially located at so in this case, right, it's going to be initially located at, I'm going to expand out what the value is, and we guess the horizon radius to be 0.3, and we ask it to store the information on spherical surface 0. Okay. So if I instead had done this, where I set up my spherical surfaces such that the first one is the one that stays static, and the second one is the one that will contain the horizon, then I need to change this one. It says which surface store info to 1, for example. And then it will know to store it there. And then, yeah, so as far as I know, these are, I guess, not necessarily the same thing. So from what I read from the documentation, origin X tells me where is the refinement center located. So it's associated with what carpet regrid 2 set. And then this one tells me where the actual center of the horizon is expected to be. Is that true? But I need to set them both, otherwise it doesn't.
You need to set them both.
The origin X is the center around which the strahl curve needs to be located. That is uses to find the horizon, and then center, that's just wherever you put the center of your initial guess.
Yeah.
You can like center your sphere off of where you're centering where you're looking, which directions you're looking for the horizon, just to be confusing.
Yeah, just so that, why not? And then luckily quasi-local measures is much easier to set up. The only thing that you need to remember is to set it to verbose, because I mean, of course, it will still produce the files that it produces, but otherwise you see no information that it's even running, as far as I can tell. So I like to set verbose to yes, so that at least it gives me a summary of what it found. The number of surfaces that I wanted to compute things on is 2, and then I wanted to compute things on both surface 0 and 1. So that's why it's set up this way, right? So it will perform integrals at the surface of at the horizon surface if AH finder direct finds one. If it doesn't, it will just skip that surface. And then it will also compute the integrals at this surface located at 1024, like I said there. And then finally, I set up as minimally as possible this the IO ASCII thorn to just output 3 things. Well, it's actually going to be more than that, but it's just going to output the 1D version of the lapse function, the 2D version of the lapse function, and the quasi-local measures scalar. So it's going to give me mass, spin, and things like that, which it's not really a scalar, but whatever. And then these thorns, like I said before, just have to be there because they have to be there, right? And that's it. So I could not write this from scratch again, even after giving this talk, because it's just, anyway. Okay, so what happens with this? So, okay, yes.
So you said the possible measures to these 2 surfaces. So say this is not an initial black hole, say it's initial neutron star and collapse your black hole later on, and find that horizon. So is that your quasi-local first start off with this giant 81?
Yeah. So it's so if you set up quasi-local measures on a surface that has been given to AH finder direct, if quasi-local measures is called, it looks at the surface. If there is no horizon data, because AH finder direct told it that there is no horizon data, it won't do anything. It would just skip it.
Oh, just skip.
It would just skip it. Yeah, it will say no valid horizon data found, skipping surface or something like that. I've seen that many times while trying to set this up, but that's what it does. And then on the other one, no. On the other one, it will keep trying to do it, right, over and over. And I didn't do this here, but there is an optimization that you can use when you're doing binary neutron stars, especially if you have done it before, or at least you have a rough idea of how long it's going to take for the stars to merge. You can tell AH finder direct to only start looking for horizons after time 3000 or something like that. And so before that, it won't spend any time trying to find something that clearly won't be there, right? So
that output file is just starts like say it merges it collapsed at 2010 it start T like at 2000.
Yeah, that's how it starts. Even like even if you don't set that up, it's not going to output anything until it actually finds a horizon. And then when it does, it's going to be completely discontinuous. It's going to have nothing, and then it's going to have one iteration 200,000 or something like that. Yeah. It only outputs if it finds something. Is there any question? Yeah.
I mean, this could wait till the end, but can you explain the actual like output, like?
Yes,
0D1?
we will look at that now. I will actually run this bar file, and then we will look at what comes out of it. Yeah. So I'm cheating slightly here. Let me just make sure that. So I'm moving now to a Linux machine. Of course, it didn't work. That is located in my office. That's not what I want. And the reason for that is both because that machine is faster and because I had a few problems running this earlier, and especially for the second part of the tutorial, I need it to be a little bit beefier than what this laptop is, and so I'm gonna skip it to there. Okay, let me just make sure that, okay, X11 is available, okay, code T. So let's go here. So this is already, I'm cheating a lot here, right? So if you download the repo, the PAR file comes with it. The executable does not, right? So the executable, I already pre-compiled the toolkit on this machine. It is the default Einstein toolkit. It's the latest release. I didn't do any modifications to it, except that I pre-compiled it so that, you know, we could do this quickly. So I'm just gonna run that PAR file and hopefully I didn't mess anything up. So it's going to be pretty fast because, you know, like I said, this is not production ready by any means, right? So, okay, if you don't set up, for example, verbose for quasi-local measures, you're not going to see any of this information down here. It's just going to, the last line will be here, right? But this already tells you a few things that happen. So first, there's a bunch of things from NERP elliptics telling you that it's going to compute a binary black hole initial data where the mass of one of them of the black holes is 0. So it's effectively going to set up only one. The bare mass of that black hole is going to be 0.5. It's going to be located at x equals 0. And it's going to have an angular momentum along the z direction of 0.2. So these are things that we kind of want to see later, right? So located at 5, the mass is going to be 0.5, and the momentum along the z direction is going to be 0.2. Here it's already also nice to see it found a bunch of refinement levels, so that means that our PAR file set up a bunch of refinement levels. And here starts the calculation, right? So the first thing that you see is that Finder Direct is searching for a horizon. There are ways to make it more verbose than this. I just set it to the default because I wanted to show as few parameters in there as possible to try to confuse you as little as possible. But you see that it actually found the horizon. It gives me the radius. I gave it a guess of 0.3. It actually found one that the radius is 0.25. And it says to me that it's located at 4.999 something and 0.000 something, right? Which is consistent with what we set up initially. It was at 500, at least 4 significant digits, I guess. And then once we got to quasi-local measures, it's now computing things in 2 surfaces. And if you remember, we switched just to see what it would do. So the first surface is actually located at the outer boundary, right? And it's going to be computing, yeah, I think that's correct, right? And it's going to be computing basically ADM integrals at the surface and other things. But it basically finds that, you know, the angular momentum along the z direction on the grid is 0.198, which is somewhat consistent, right? We had one black hole with a spin of 0.2. It found a mass that is a little bit larger than the 0.5. And then when you get to the second surface, I don't remember if it actually says that it found a horizon somewhere. Does it say like horizon data? Does it inform us that it's actually computing something in the black hole? I don't think so, right? Yeah, it's not telling me that it's computing.
What does that for negative ADM?
I don't know. So yeah, I don't know why it's negative. Maybe it's just because the resolution is too low or something, but I don't know. But the momentum are all good and the ADM energy is consistent with the bare mass, but there's some, like this mass is 500. I don't know what that means, right? So
yeah, so this is only valid at integrals as R goes to infinity. Purpose integrals R goes to infinity. So yeah,
so these are not
unfortunately, no, it's not. It's ill-defined. In fact,
right.
Yeah, these are R goes to infinity surface integrals.
Okay. Yeah. Yeah. So you see that this provides a simple. So this was just the simplest case that I could think of to start things off, which is, you know, just set up something and the simulation died. We did not have to worry about setting up any evolution thorns. So we did not have to worry about doing MLBSSN and or bycall and everything else that is associated with doing things like that, right? This is just as simple as I could imagine a PAR file to be. And then the good news is that moving from this to an actual binary black hole is very, very, oh, sorry. So let's first look at some of the data, right? So if you now check the parameter, so I didn't even tell it to dump things in a directory, right? For the sake of not having to import another thorn to activate another thorn and configure it. So it just dumped everything that it found here. So the first thing we can look at, which is perhaps one of the things that people like to see sometimes, just to make sure that things are set correctly, is did we put the grid in the right place, right? So one thing that I like to do, especially when you deal with these very large ASCII files, is I always try to open them with less, because less won't try, I don't know exactly how it does it, but it's very lightweight compared to trying to open it with Emacs. For this one, it probably won't be a problem, but if you had a simulation running for days and you try to open something with Emacs will usually prompt you with like, this is gonna take like a while to open, but less always opens it instantly. So so I just open here this out XY. This contains the laps at the XY plane, so at Z equals 0. And here there is a header file that tells us a little bit about what the file contains. So for example, it even tells me what each column means, even though some of these are, I never use them, so I don't know if it's important. But for example, the first one is going to be the iteration. Second one is the time level. Is that, I don't know what that, what's the use of that very much. But the third one is the refinement level. So I usually find that useful if I just want to plot a single refinement level. That's the one that's going to filter it out. Then I don't use any of these normally, except for this. This is column 9, even though it's not obvious because the spacing is weird. This is time. And then the ordering always goes X, Y, Z function. So that's the ones that I always remember are columns 1, 3, and then 9, 8, 10. Sorry, 10, 11, 12, 13. Those are the ones. And they are all same here. Like, so there are a few things that you have to be worried about. I mean, not worried, but keep in mind, right? There are ways to set up the IO thorns so that they group grid functions together. So usually, for example, the metric in the ADM base metric, it's actually defined inside a group called ADM base metric. And in there you have GXX, GXY, GYY, all the components of all the 6 components of the physical spatial metric. If you ask them to group things together, you only have one file called metric.xy.ask, and then you have extra columns in this file now. We're going to have column like 14, 15, 16 for all the components of the metric, as far as I know. And there's another format which is called compact format, which I never used, but it changes all the column numbers. So it's very, yeah. But anyway, it's something that to keep in mind, right? The ASCII file format can change a little bit depending on what you do. Yeah, and this grouping also affects the HDF5 stuff, but I don't think the HDF5 has a less verbose option, is there? Yeah, that one just has everything that it needs, right? Yeah, okay, so that's just one thing to keep in mind. So I'm going to show you how to, okay, so if you scroll down a little bit, or you just go to the bottom of the file, if you're in less, you just press capital G, you see that one thing at least makes sense, right? The last refinement level is refinement level 10. That's because it starts at 0 and we had 11 refinement levels set up. So it does have the 10 refinement levels. So I use GNU-plot a lot when I want to see things quickly, especially when I'm working remotely, like on a cluster. And so I'm not going to do GNU-plot to generate the plots at the end of the tutorial, but for now, all we want to see is look at a grid. So I'm going to do that. So if you remember, column 10, 11, 12, 13 have X, Y, Z and the data functions. So I'm just going to plot X and Y. And I'm going to plot that with points. And what that's going to give me is the grid structure. There are probably other ways to do that. I think you can ask the coordinates to be output, but I normally don't do that. So I'm just going to do. So for those that don't know GNU-plot, it just says plot using columns 10 and 11 with points, and you can see a double W there, of course. And I can do title, grid, structure. Okay. And then hopefully we'll be able to see it. Okay, there you go. So this is the grid structure, and of course it looks okay. Is it view square? I don't remember. No.
Size.
Set size. There you go. Because otherwise it looks like it's not square. Okay. So now you can see that there's only one refinement level. Sorry, one center, right? And then I can zoom in, plot allows me to do that. So I'm going to zoom in a little bit here. And then I'm going to zoom in a little bit more. And then a little bit more. It's better if I just zoom in at this inner one, because otherwise it's going to take forever. Okay, and you see all the refinement levels that we set up are there until we get to the finest one. And in the next example, you see actually two little things. But yeah, so the grid is there. And so there are a lot of annoyances with dealing with AMR data, right? So for example, let's say you want to see the lapse along the x-axis. It's a fair thing to want to see after you set up initial data. So if you say, okay, why don't you plot me the lapse? So 1D, 2D, and I assume 3D, I never really worked with 3D ASCII data. They always have the same format. So long as you remember that columns 10, 11, 12, 13 contain X, Y, Z and data, that will be valid for all ASCII files that are in this long format, right? So if you say, okay, plot the lapse now, right, with lines, okay, the first, unfortunately, because the grid is so big, right, it gives too much. So I can actually set, is it X linear or X range? It's range, right? Yeah. So I can set it so that it plots it from -2 to 2, and then replot. And then you can see it's just a mess, right? Okay, you can't even see anything because it's just, why is it showing like this though? It's showing in a weird format. Sorry, I'm gonna zoom in a little bit because it's looking weird. But you see that the problem is that when you plot it like this, all of the refinement levels are being plotted on top of each other because, plot has no idea what this is, right? It's just plotting data as you give it to it. And so one way, unfortunately, I can't tell it for that window to just stay on top. So I have to, okay, just a second. Okay, so one thing you can do, and of course, if you're using Python for this or Quibbit, which is suited for these things, you don't have to do this so manually. Sorry, technical issues here. Oh, okay. Is it gonna reboot? What? Start sharing content. Starting it. Yeah, I did say just technical difficulties. If you guys can still hear me, just bear with us. The projector turned off. Now it probably share USB-C. All right, there you go. Okay, so now I mean, I know that this will sound like voodoo, but the way I do it is I remember that third column has the refinement level. So I can say, for example, why don't you plot this only if the column number 3 is equal to 10, right? And then I have to put these things to say to me the column. And then if it's not, just don't do anything. Just plot nan. Right. And then that's just giving me the finest refinement level. And then I can change this to plot any refinement level that I want. And of course, this all sounds great, but this is because this is a very small ASCII file. If the way that these things happen is, okay, I just dumped 11 refinement levels for iteration 0. And then my next dump will be on the bottom of that. And then the next one on the bottom of that. So these files are going to get very big, very fast. And they become a nightmare to work with after a while. So that's why Quibbit is very good at sorting like the HDF5 stuff. But the ASCII files are just very convenient for plotting things quickly like this. And yeah, and then we can also look at the lapse in the 2D plane if you want. But I'm going to skip that part for now because I think it's not particularly useful for this part. But anyway, so that's, and of course I missed and then there's the horizon date, right? And there's of course all of the things that were output by quasi-local measures. The horizon data are typically available in 2 forms. So in this black hole diagnostics, you're going to have a lot of information that I'm not sure which thorn produces this. Is this HDF? I don't know if it's okay. So this is the AH Finder Direct. So there's a lot of information here regarding the horizon if you want to see it. But then there's another one, which is the one that is actually useful for plotting, as far as I know, which is this H.T0 blah blah blah. So the zero means the iteration that it actually found the horizon. So if you do it for a binary black hole simulation, that only starts appearing after a while. But if you look at this file, it has a different format from the standard grid function formats. And this is like a patchy grid. It's 6 patches or something, if I remember correctly, that for setting up the horizon. I think yesterday Gabrielle was showing like when you plot it, it only starts plotting in a few sections of it. And it basically contains 3 things that I don't normally use. And then it contains X, Y, Z for the surface of the horizon. And the beautiful thing is that it's very suitable for plotting with GNU plot again. So if you just open GNU plot and now you have to set it up to plot 3D data, and you say set view equal XYZ, just so that because otherwise it would like squash things because it would just set the scale all wrong. And now you do splot, which is it's the lingo for 3D plotting, and say using 4, 5, 6 with points. And now you have the horizon data that it found, and you can even spin it around, even though it's very slow because I'm doing it remotely, right? But yeah. So
hey Leo, can you plot with lines?
With
It
lines?
looks very beautiful.
Oh, I didn't know
Yeah.
that. Oh, there you go. I didn't know it was going to look good.
Yeah, zoom in a little bit and you'll be able to see the 6 patches.
Yeah. Yeah, I guess it's kind of somewhat visible already that there's like a patch here and a patch on top and a patch there. I don't know much about visualizing 3D data like this, especially when it's this laggy, but you can kind of see there. But yeah, so this is a simple way of plotting this. Now, usually, like I said, normally I use this to inside a Python program to just plot the horizon surface. I'm unfortunately not going to show that today because it involves some magic that I don't really understand with Python either. But because because there are a bunch of patches, you have to configure it in a way that works. And I'm pretty sure that Quibbit knows how to do that much better than I can. But the only way I know how to do it is to do it very manually. So yeah, and then of course you have all the files for the spin and the momentum. And you can use this to do a series of plots. And right now we only have 1 point in each of these plots because it's just the things at iteration 0. But this would give you time series of a bunch of scalars that are very useful. So now I'm just going to quickly go over the binary black hole parameter file, and hopefully we can agree that I'm not going to close it.
Just a question on this stuff.
Yes.
So the 2D output, like X will output along some Z slice, right?
Yes.
And then so is it 1 slice per refinement level? Or how are those slices chosen?
I mean, you're gonna have, we're gonna have data on that slice for all refinement levels.
Okay, but then how are those slices chosen?
And so if the grid crosses 0, it's gonna be Z equals 0 plane.
Okay.
But because this grid doesn't cross 0, it's gonna be I don't know if it's the closest to 0, or I don't know how Carpet decides that, or the IO forms decides that.
Yeah.
Because if you don't have the at 0, it's not gonna interpolate it to 0 and dump it. It's gonna plot, but I don't know if it's the closest or if it's the the one to the right of it. I don't know exactly how it is.
Like there's those products, I'm not 100% sure either.
Yeah. But yeah. Okay. So now I just wanted to open up the binary black hole example, which I'm not going to type everything again. I'm just going to say that this list of thorns is identical to the previous one. And the setup is identical again, except that here I now changed so that the puncture of the second puncture has also mass 0.5 and also has a spin in the Z direction of 0.2. And it's located at -5 instead of so now we have 2 punctures with bare mass 0.5 and spin 0.2 in the Z direction, located at And again, this is very low resolution. I'm not trying to focus on the initial data thorn. I'm just trying to show you that now that this will be sufficient to produce 2 punctures. This doesn't change at all. I'm still going to have 11 refinement levels. All the setup is exactly the same, except that now I have 2 centers. I want 1 center around each black hole. And so the first center is located at plus the foci position. The second one is located at negative the foci position, because that's where I'm keeping the black holes. They have exactly the same setup. If the black holes had different sizes, you might change the radii a little bit to accommodate for that, but I didn't bother to. And now, unfortunately, the font size is gonna bite me a little bit, so I'm just gonna try to. It's probably gonna be too small. Anyway, so now I'm setting up 4 surfaces just because why not? And the 4 surfaces that I'm setting up are 1 for each horizon, then 1 at the maximum radius, and then 1 at the intermediate radius. This is what you typically would do if you want to extract gravitational waves at different radii, for example. So I just want to set something like that, because why not? Yeah, and then now I tell Finder Direct to search for 2 horizons. You typically find in binary black hole simulations that are typically there's a search for 3 horizons. It's the individual horizons of the 2 black holes, and then 1 is usually centered at 0 or something, and always tries to find a common horizon of the 2 once they start merging. I did not bother to do that because there's not going to be an evolution, but keep that in mind. And so I just say, try to find a black hole located at the position of the center. And if you do store that information on surface 0, and then the other one, if you find it, it's going to be located at the position of the other center. And if it finds it, store it at surface 1. And then I ask quasi-local measures to compute its things on all 4 surfaces. And that's it. These are the differences between the 2 part files. So really, I only added these lines, and I added a few extra stuff to the configuration of some of the thorns. But in general, it was very easy to do this, right? But in practice, there's going to be a lot more configuration for a lot of these thorns. One typical thing that you will see, just as a heads up, is that most of these thorns use 2nd order interpolation by default. So almost everyone will change that to something higher. Some people might like to change the interpolator name. So it might change from Lagrange to Hermite or something like that, and that's an option. And so the configuration for these thorns get very large, right? And just keep in mind that this is something that should at least give you a good idea of what the thorns are doing before you go look at something that is a lot more complicated. But at least okay, these parameters do that, and everything else is just trying to make things a little bit better. Yeah, and I didn't change anything else, so the output is still the same and everything. So now I'm gonna go back here to the binary black hole example, and I'm just gonna run it. You'll see that the runtime is actually basically the same. It's not gonna change much because the resolution is very low. Okay, it already finished. And then, you can see that it again finds now it found the 2 horizons. It says that one of them is located at +5 almost, and then the other one is -5 almost. Sizes are the same, which is what we expect. We expect the black holes to be identical because they have the same bare mass. You found the spin to be 0.2 and the spin and momentum in basically 0, let's say it that way. And the total spin as computed in the 2 surfaces that are at half the radius of the biggest spots and largest radius is going to be about 0.4. So what it found down here and what it found down here. So, okay, so this was just a very simple thing to show. And then if we want to repeat one of those, I don't know why my computer is doing this now. So before, right? Whenever I tried to open the new plot and you needed X11, it would open X quartz automatically. Now it doesn't, and then even when it does, sometimes X quartz stops responding or something like that, and then I have to do this thing. So I have to keep relogging in to refresh the connection for some reason. Okay, so now if I replot the grid structure plot that we had before, you see that at first glance, it looks exactly the same. And that's just because the two centers are distant from each other by 10, right? One is at +5, the other one is -5, and this grid goes out to 1,000, and GNU plot is showing even at 1,500 here, and so you can't even see that there are actually two refinement levels until you start zooming in. So if we start zooming in here, our two refinement centers in. So if you start zooming in, eventually you start to be able to see that the two centers split up. So there you go. And also the carpet is, as far as I know, carpet is smart enough to realize that even though you requested two things, it will kind of merge refinement levels together when it can. Is that true? So like this becomes one big patch while there's overlap between the two, right? You don't have to specify that. And then but as the black holes move, if for some reason you're doing something that the black holes will move further apart, when they're far enough apart, those will become two separate centers at all levels if needed. But yeah, and then as you keep going in, you just be able to see all the refinement levels that we set up. But it will become more and more distorted if I keep going in, so I won't bother to. But yeah, so this is just, I just figured that it might be, these are very common thorns that everyone uses on pretty much every simulation. I figured that it might be useful to just provide an overview of how to set them up. And now at the end, very quickly, I just wanted to show you, something that I normally have to do a lot, which is, okay, we did a simulation and now we want to visualize what happened. Sometimes that involves computing other things from it. And so the data that I'm going to show you is actually completely legitimate data that was used in a recent publication. But unfortunately, because it's very large, it's not really available to you yet, I would say. Maybe we can put it somewhere, but for now, you have the scripts, but you would have to provide your own data, which I know is not very useful. But so this assumes a little bit of a setup, which I will explain later. But first, I wanted to just explain what is happening. So I did document this on the wiki. So there are two things that I want to show you. The first one is how to do a movie for the fluid density. So this is for a binary neutron star simulation. Sorry, I changed topics way too fast. But this is for a binary neutron star simulations performed with Illinois Germ HD. The parameter file is significantly more complicated than that. So this is not a Jupyter notebook, so it's not interactive, but this is already available if you want to go there and see it. And the idea is that, this little tutorial tells you how to search for grid function data in a directory where you perform the simulation, then read it in using Qubit, preferably from the HDF5 files. Then how to interpolate the AMR data, which is all that complicated thing, into a patch that is of uniform resolution, which is usually means it's just a single grid and it's much easier for you to deal with. Then it teaches you how to do unit conversion. That's something that a lot of people ask about, and it's something that I've already written something like, as you see below, that I always use to figure out the units. How to generate images. This is the part that I depart from Qubit because I'm not that experienced with it. And then how to generate a movie from the images, right? So I have some information here regarding the directory structure, but I'm going to skip that for now and focus more on the code, right? So I'm sure Gabriel already gave you a pretty good explanation yesterday, and this will be a lot of repetition, but just a quick overview. You can import this class from Qubit called SimDir, simulation directory, and it will search a simulation directory for any data that you can possibly find. So in the way that I set it up in my computer, you have these output directories, which in practice, in the cluster where they actually live, are full of data. But in here, I only really copied the data that comes out of Illinois Germ HD. So this is an example of a combined file, like I said. So Illinois Germ HD has a bunch of primitive variables, and typically these would be separated into the rho variable, the velocity variable, so in the x direction, velocity in the y direction, velocity in the z direction, and so on. That's what I normally do with the ASCII files because I find it easier to look at it. But for HDF5, we can just put everything in one directory and Qubit will know how to do it. So that's what I did here. So this will contain all of the primitives defined inside Illinois Germ HD, except for the magnetic fields. It's a separate output file, which, yeah, anyway. So you need to know what variables are in there. There are ways to ask Qubit to probe it, but for the sake of it, I'm just going to show you one way to do it, right? So in this case, I provided it what is the name of the output directory. I'm assuming that there's this output directory here. I tell you, please create this object simdir in that directory. And then you see that sim has I don't know, it's a property or a member function in there that's called GF, and that's the list of grid functions that it has. And then it also has this thing called XY, so it's all the grid functions that live on the XY plane. And then in there, that's like a dictionary, and then you can say, okay, give me grid function row B. And if you didn't know what it was, you can just print this object sim. So this is all Python code, of course. You can just print that, and this is, for example, the output that comes from the code. It will also tell you everything that it didn't find, but I'm just specializing here to what it actually did find. So these are the grid functions that are actually available from those data sets, right? So now I want to interpolate that onto a uniform grid. So again, I'm just saying, okay, the grid shape is going to be 401 points, because why not? Both in X and Y direction. And then X and Y are going to span from -100 to 100. And Quibbit will figure it out when it needs data from the finer levels and when it needs data from the coarser levels. I'm going to gather all the iterations that I have available in the data set. Now you see that I have 20 output files, and that's because this simulation took 20 restarts. And each time there was a restart, I stored the data in a different directory so that they didn't get corrupted in case the simulation died, which it did. And some of the data got corrupted, but not all of it. And so instead of saying, use iteration 0, I always say use the first iteration. For this example, use the first iteration available in that file, get the time associated with that iteration. And then, from all the rows, give me the row at that iteration, and then interpolate that row to the uniform grid that I specified above. And then the last step is give me X and Y on that uniform grid as well, because I want it, right, for plotting purposes. And you might not need that if you know how to use Quibbit, but because I don't, and the next part will be very manual, I need all of this information. So, okay, unit conversion. So unit conversion is something that I do very often, right? So for this particular simulation, I know that we adopt units where G, the gravitational constant, is equal to C, the speed of light, is equal to the mass of the sun, is equal to 1. So these are the units that we've chosen. It's the units that, for example, are adopted when EOS Omni reads in a tabulated equation of state. And that's what we do. So we know now that we have to, everything is dimensions, right? When we plot it, we're going to plot X, Y, and density, and everything is dimensions. So if you want to restore units that are usually useful and quoted in the papers, where like X and Y are in kilometers and the density are in grams per centimeter cubed, you have to put those units back in. And so we just find combinations of G, M sun, and C that have units of length, time, and density, and just restore it as we want. Right. So I use AstroPy for this. I'm sure there are other ways to do it. But I find it very convenient, especially when we do analysis in Python. So AstroPy has values for a bunch of physical constants, and I import G, C, and mass of the sun. And then I know that this particular combinations of these quantities will yield me units of length, and then length divided by C will give me units of time, and then mass of the sun divided by length cubed will give me units of density. And then I just ask it to convert to whatever units I want. So I want length in kilometers, time in milliseconds, and density in grams per centimeter cubed. And then to restore, you just multiply everything by the appropriate constant, right? So I multiply all the uniform row data by the density value, the time by the t value, X and Y by the length value. And I have to do this before taking the log of the density, which is what I will ultimately plot. And then this is the part that Gabriel will probably bang his head against the wall, because I'm sure there's a way to do this much easier already with Quibbit, and I don't have to do any of this, but then I just manually import now matplotlib and do the plot myself. And yeah, and then there's nothing really to it. I use bcolor mesh to plot this XY row. Vmin and Vmax just set the range of the color bar. I choose a font, I'm biased to the new plot, so I always choose the color map of the new plot. And I put some decorations here and there just to say what I'm plotting, right? And this is what it does. It doesn't look great yet. The axes are not, the figure is not squared or anything, has more labels here than it has here. So I'm not happy with this plot, but for a minimal example, it does it, right? And then to generate a movie, I just run this command that I copied from somewhere. Yes.
Just have a quick question. So Qubit is very similar to PostCactus, right?
Right.
And, in PostCactus, I think you have to, if you do, I usually do like this too, you
Mhm.
finally import things,
Mhm.
but I need to plot the transpose of the data. So
Oh,
is
I
that
see.
the case here?
I think this is correct because the punctures are supposed to be on the x-axis, and I think if it was
Right,
wrong,
so
there.
you didn't do any.
Yeah, no, I just,
Okay,
yeah.
okay,
I assumed that when I did this, I would actually get X and Y. So, and I guess I did. So,
okay.
yeah, but it's a good point. I already had problems like that before, especially if you use imshow instead of pcolor mash. Imshow likes to switch the axes as well, and I don't know how to fix it. So, yeah, so
I use the intro. Okay.
that might be it. Yeah. So, and then, yeah, I copied this from Stack Exchange at some point, and it always worked, and it stays in my history, and that's what I used to generate the movies, right? So I broke it down so that you can kind of understand what is the logic of what's being done. But in practice, I provide also one script that you can run, and it will loop over all the iterations available throughout all of those files along all of those directories in parallel. And it would generate all the things that you need. And then in the end, you still have to run that FFmpeg to generate the images, right? So that's what we're going to do now. So I gave the option of generating it in parallel, but this is one of the main reasons why I had to move to Linux. My installation of multiprocessing is not working on my Mac for some reason on Python 3.11.1. So Linux, it is. So this is, so I already have some things there because I was running it before. So I'm just going to delete these images so we don't have to worry about it. And then this is just, okay. So this will give you an idea of how long it takes to process, a simulation that took about a month to perform, right, with Qubit. And hopefully if everything goes smoothly, which it doesn't look like it is, it should take only 2 minutes. Why is it stuck? Sorry, let me just check. No, it should be fine. So yeah, so for each directory in the app, so this is the thing that you would have to change if you actually want to use this particular script, right? So for it tries to find all the directories that are named output underscore directory underscore something, sorts them out, and then goes into each directory and reads in the HDF5 file with Qubit and then performs the interpolation. Why is it not outputting?
So why yes, can you unset the display variable?
Sorry?
Can you unset the display variable?
Sure. Oh, that might be it. That's true. Yeah. So just set it to 0.
Oh, unset. This will unset.
Yeah, that might be it. Yeah, there it is. Okay, so it even though it's multi-threaded, right? It's not the best multi-threading. It's gonna go into one directory and then process. Each thread will process one iteration from HTML5 file that it opens, but it's not going to open each file in parallel or anything like that because I couldn't figure out how to do it very quickly. But this is quick enough. And like I said, this is what I would normally do, except that instead of running it on like my office computer, it would just be running directly on the cluster where the simulation actually be performed. And then the only step that I would have to normally do is I would have to tar everything, all the images into one file, send it back to my office computer or my home computer, and then create the movie there, because usually I don't have access to the FFmpeg. And I know there are bindings for Python, but if you don't have access to the actual movie generator, there's no point in having the Python binding. So that's why I didn't bother to do that in the script. I try to keep it as real as possible to what I normally use. Hopefully it won't take too long. And while it runs, because we don't have to keep looking at this, I give another example where instead of just doing this, right, instead of simply plotting the density, what if we need to actually do something with the data? So for example, Illinois Germ HD evolves Vx, Vy, Vz, but sometimes people want to see what does the radial velocity look like, right? And of course, there's this, strictly speaking, this is not really the radial velocity. There's a metric thing there, but this is good enough for the sake of the tutorial, right? There's an extra parenthesis here, but whatever. So assume that the radial velocity, you know, we're in flat space, and then this would be correct. We only have data on the XZ plane. So I'm going to just set this last term to 0. So the radial velocity that I'm really interested in computing is something like this. And so the steps are exactly the same, except that I'm going to have to read 2 grid functions now. And then after I actually have the raw data for those grid functions, interpolate it onto a uniform grid. I'm not going to deal with the AMR data directly. Then I'm going to compute the radial velocity and make a movie of that. So it's the same steps. Probe the directory, import 2 grid functions now instead of just 1. Then I'm going to keep the same grid shape and extent that I had before. Read in, you know, Vx and Vy at that given iteration, the first one that it finds in the file, for the sake of this example. Then interpolate both of them to a uniform grid and get the X and Y grid. And of course, because these are all the same iteration, I assume that everything is the same for all of them, so I don't have to keep doing things separately. And now I just compute VR. So I convert the time, the X and Y to their appropriate, I restore units to them. I'm not going to restore units to V because V is in units of C, and it's usually typical to just keep it down as V over C. And so I'm basically just going to do, okay, these are just NumPy arrays, right? At this point, these are all NumPy arrays, so you can do NumPy calculations. So if this is X in kilometers and this is Y in kilometers, then this is R in kilometers. And I cheat a little bit and I add a little thing here because I'm going to divide by R and I don't want to divide by 0. So I just added a small thing here. But when R is 0, X is also 0, so it's not going to affect anything. So now I have Vx and Vy, and I just use this expression here to compute the radial velocity. And then I generate the movie again, and this is sort of what it looks like at a later time, right? It's the same steps as before, and then I provide a script to do exactly the same thing where it does all together. So hopefully I'll be able to, okay, see it took a minute and 41 seconds to do the row one. And then this is the one that does the actual velocity thing. And then I promise I'm done after this, but at least you'll be able to, you know, watch the process of generating this in real time. And while that's going, because it's going to take 2 minutes, I can actually tell you what normally we have to do, right? Because for the longest time, we didn't have HDF5 data because we didn't have a tool like Quibbit to work with. And so what we did was we worked with the ASCII files directly, right? So the good news is that Zach actually went to the trouble, Zach Etienne, my supervisor, he actually went to the trouble of writing a carpet interpolator in C, or C++, who reads in the data file one time level at a time and interpolates that to a uniform grid. And it's actually pretty fast. So, but you still have to compile a separate C program, run that first, then run a Python script on top of all the files that it generated for all the files. So it's much longer than doing this, right? Having the HDF5 files is like what normally takes your 2 minutes to generate the movie. It would take me probably 15 minutes just to do the interpolation, right, of the ASCII files. It takes a long time. So yeah. Yeah, unfortunately I didn't run this on screen, so I can't start making the movie while the other one runs. But I think actually
yeah. Leo, can I make a quick comment?
Yes.
So when it comes to generating this sort of connective tissue, like what we're seeing here, where you're going into each directory individually, parallelizing sort of with multiprocessing the generation of these PNG files. I found that ChatGPT is amazing at generating some of this stuff. Basically, you just tell it in English what you want, and it will output in Python. So, for example, you could just tell ChatGPT, okay, so I have a bunch of files and a bunch of subdirectories. They look like this. Write a code that runs this script on each file, but in a multiprocessing context. Literally, it will do that. And then we wouldn't have to, it would be faster, in other words, than this, right? Here we're waiting on the one that takes the longest in each directory.
Yeah.
But
because basically once you go into one directory, that, for example, this computer has 16 threads, the 16 cores to actually work with, right? So I span 16 threads at a time, if possible. But if there are less than 16 iterations in an HDF5 file, a bunch of threads are just sitting doing nothing, right? And so you could, in principle, parallelize this better than what I'm doing, but I didn't bother to do that. Okay, so it took 3 minutes. But yeah, thanks, Zach. That's true. And then let me see what I have. Oops, that's not what I want. Okay, let's gonna do that. All right, and now I go back to my computer. You won't be able to see it unless I go to the temp directory. Then what I do, so this is, again, I'm really doing what I would normally do, right? So now I copy things over SSH from wherever I use to generate the data from over to my computer. And I'm not really checking these carefully because I already did this earlier, so I know that this will work. And now we can actually look at what the movie looks like. So it won't look great, right? In the sense that it's a little bit too far, it's a little bit too stretched, right? They don't look exactly like what I wanted to do. But you know, for something that we did in 3 minutes, that's pretty good, I would argue, right? And of course, it's not plotting the horizon data, which is something that, you know, a production script would do, but it's something for you to start with. And I'm pretty sure that if you look at what Gabriel has in the tutorial for Qubit, there are many ways to do that. I apologize if it's laggy for people online, but here it looks great. Yeah, this is the radial velocity. So you see that after they merge, there's a burst of fluid outside, and then after it settles in, the velocity is inward, because things are starting to flow inside a black hole that forms, even though you can't see it. But yeah, so that's it. You can find all the scripts in here in the wiki for that repo. You can also find them in actual code form if you prefer. You don't have to just copy paste from there, right? I have so inside the binary black holes, you have the PAR files that we talked about, and inside the binary neutron star, for now, you only have the Python. There are copies of the movies in resources, and here you have a copy of the Python files to process the VR and DR. So if at least it should serve you as an example of what to do, if you want to use this to generate similar movies. So yeah, that's it.